Hello everyone, this is the solution video to homework 3. Now, um, we have a third order transfer function with 2 seconds of delay, and the first part of our first question is about stability, and then the second part is about the PiController, and then we also have a second question where we have the state space. So, let's dive into it. Now, we are asked to look for the body plot. So for the body plot, we're going to get the body plot, we're going to plot it, and we're going to look for specific points on the body plot. So let's dive right into it. Now, we can get the body plot using mag, faith, and omega, calling the body function here. Now we are going to add, I have separated the delay part and the minimum phase part and the delay part here, but yeah, I'm multiplying them, so there's no big deal in it. So let's call it part 1 and body. So if we use this, you have to use squeeze here, since we since the body function here deals with multi-input, multi-output systems, and we're only dealing with SISO systems, single input, single output systems. We have to get rid of the unnecessary structure here. And now we have our body plot. So let's create a figure. Let's hold on. Let's plot omega comma mag. Of course, we need to use subplot here. CLA. Hold on. Grid on. X label would be omega. And Y label would be then the magnitude here of g omega. We also need to set the x scale to log, so that we have a logarithmic plot here. And ax1, GCA, so plot ax1, line width of 2, maybe a blue color. So we're creating the same thing here, but now we have the argument instead of the gain. Of course, this would be phase. So this is quite basic. We will do this for almost all the body or frequency domain approaches here. So now, since we're interested in stability and the stability interval of this system, we need to look for a specific phase angle. So let's call this an error, and let's take the absolute value between minus 180 degrees, and the phase vector here. So I'm going to look for the value and index where this happens. Actually, I'm not really interested in the value, but in the index, I'm looking for the minimum of this error here. And the reason behind that is the following. Most of the time, we have numerical data when we use body plots. And due to that, we need to actually look for the nearest value. So I cannot directly search for equality. I need to search for the minimum error or distance here. So that's the reason why I'm doing this basically. Once I have done that, I'm going to look for actually the K value here, at which frequency this is basically happening. So I could display the frequency here. So omega is going to be string omega index, and then we would have kval, which would be 1 divided by gain index here. There we go. Now let's also display that maybe. So let's have k and then also k-val. There we go. Now, this is not the only point that I'm going to be interested in. The point that I'm also interested in would be the angle where it is equal to 0. The phase angle being 0 is also important here. And I'm going to explain why that is. And I need a -1 here because now I'm assuming that we will have negative values here. Actually, I said it, so let me repeat it. If we are looking for positive k values, then we use -180 degrees. But if we are looking for negative values, due to the negativity, the angle contribution is due to the negative sign, so that would be -180 degrees. But then we are looking for basically 0 degrees contribution because we have already the negative part sorted out. Therefore, we look for 0 degrees, and therefore I also need to add this negative sign here because, well, I assume that k-val is negative. The gain here is positive, so 1 divided by positive is not cutting it. I need to have -1 divided by that. So this would be then the other bound that I'm interested in, and this would be exactly the same. Of course, it seems like doing this before the other one makes more sense because this is the lower bound, this is the upper bound, and we'll see what's going on here. So let's run this. By the way, I could have also plotted these points on top of the plot here. So let's quickly do that too. Plot omega index, and then we also have an issue here. Oh, it's called mag, isn't it? Yeah, it's called magnitude. So k-val is magnitude, k-val is magnitude. Okay, now on AX1 we will plot omega index and then mag index, I guess, with line width of 2 and AX2 phase. So I'm just going to show the whole thing here and gonna repeat this for this one here. Since since the index is updated, this should basically update it, so we should be good to go. So we see omega is approximately 0, we have -1.25, omega is 0.77, we have 1.64, and these are the points that we have chosen. Due to the delay part here, you can see that the angle goes towards -infinity. Therefore, we have high values already here. So we need to zoom in a little bit. Hopefully, there we go. We can see that we are hitting -180 degrees there, and we are hitting 0 here. So let me just readjust it back. And we see basically the values that we should pick here. So it's 0.8, take the inverse 1.25, and this should be also correct. Seems like it. Now, using the body plot, we can directly conclude the stability interval of this delayed system. So, what about root locus? So let's continue on with the root locus, R locus, GS times GD. Let's call it R locus, and let's run it. So you can see that we have actually messed up. Let me just... So you can see that we actually cannot plot root locus of a system that has delay in it. And it's even suggesting us to use the PiController approximation because it would make more sense in this case. Now, why can't we plot the root locus of a system with delay? Well, the delay part here is an exponential term, and it kind of converts this or prevents this from being a transfer function because it's not going to be a linear transfer function anymore. In fact, we don't have even polynomials if we have GS times GSD, because we have this E term here, we don't really have a polynomial or a ratio of two polynomials. Therefore, we will not have a finite amount of poles and zeros for this system. So if you don't have finite amount of poles and zeros, how can you plot a root locus? Because the first step is to plot the poles, or place the poles and zeros on the root locus plot, but that's not possible for systems with delays. So it's not possible to conclude the stability from the root locus plot if you have delay in your system. So what about the first order PuTTY approximation? Now, I'm not going to write down the PuTTY manually, but for the first two orders you can do that. The PuTTY function here can return you the PuTTY approximated transfer function. So what we can do is we can just use GS times GSD, and I want the first order PuTTY approximation. I can just call it, and it will give you the corresponding transfer function here. Now, so let's call it PuTTY 1. So I can convert this into TF to sim into a symbolic expression. And from now on, I can just define K and omega to be real. I can look for the closed loop here. That would be K times GSS divided by 1 plus K times GSS. And I don't need the numerator. The denominator is enough. Num then TSS, and I would end up in the following. So let's run it again. This is PCS. Now, of course, I'm interested in the stability, so what I can do is I can use the following. I can get subs PCS instead of S 1I times omega, and then solve for the real part of P omega should be equal to 0, and the imaginary part of P omega should also be equal to 0. Let's see. Now you can see we have 5 different points: sol.omega, sol.k. So as usual, we are going to define k-val, convert it into double, also omega val, sol.k, sol.omega. Now we're going to eliminate the negative ones, or because those ones are not valid by definition. K-val, omega val. Let's see what's going on here. Now we can see we have basically minus 1, 1, minus 42, 0, 0.9, and 4.81. Now, since I also can now plot the transfer function here, so let me call it, well, GSD. Let's call it GSD. I'm going to take this one here, GST. There we go. Of course, it seems like minus 42 is not going to cut it, so I'm going to take this one here, which means that I can sort based on the omega val and take the first two elements out of it, because 0 crossing and 0.9 crossing will be important, because 4.81 crossing is way after that, so I'm not really interested in that. Yeah. So let's actually create another figure here. Let me just do it somewhere here, because I'm going to create the root locus plot here. So CLF subplot let's actually have x3. Maybe hold on grid on. Maybe hold on is enough. Or there we go. So what I want to do is I want to plot the root locus on AX3 of GST and AX4 minus GST. And whilst I'm doing this, I can just actually look for a 1.25 and 0. I'm going to poles and zeros, so I'm going to use PZ map here and look for feedback. So let's actually K1. Let's define that. So kval 1 and kval 2. So that's going to be the important part here. I'm going to use basically the first element of k1, actually the second element of k1 times gst, comma 1, and then plot on x4, I guess, x3. Which one did I? Oh, this is the positive root locus. So x3, the real part of poles, the imaginary part of poles, using x here, and line width 2. Repeat this for the zeros. Maybe I should also assign a color. So let's say this one is red. I'm going to repeat this for the negative root locus. So which means that I'm going to use k1 here. And here we should use ax4 and ax4. So this was the body output. So now this is basically the root locus of the PuTTY approximation, the first order PuTTY approximation. Now we can see basically that we have a crossing here, and we have another crossing which we've captured here, and you can see there's also another crossing which we didn't bother with because, well, that's not in the stability interval. We're already in stability. So now what we can do is we can repeat this whole procedure for the second order PuTTY approximation. So let's do that too. So PuTTY 2. Now we're using that and this. Now let's change color. So this should be blue, this should be blue. Here I'm going to display string k1 1 k and then string k1 2. PuTTY 1. So if I repeat this for PuTTY 2, all I have to do is I have to change this to K2, this to K2, and of course it's to K2, but I need to see what kval is. So it seems like this one and this one still works because the other ones are out of the bound. So for party 2, it seems like we're still good to go here. So if I run it again, I can see that the first party approximation gives me an upper bound of 1.86. The second one gives me 1.7, whereas I already calculated that the upper bound should be 1.6426. And this is basically the result here. It's not really easy to see. Maybe I should associate the root locus colors here too. So if I give it a B in this case and an R in this case, I might be able to separate the root locus from each other. If not, it's not really important, but yeah, let's see. So you can see the root locus plots do change, but the position where the root locuses go through the j omega axis do slightly change, but keep in mind that neither this root locus nor this root locus belongs to the original system with delay. And you can see even here that we have interesting root locuses because we're adding a set of zeros to the right half plane, a set of poles to the left half plane. There will be a transition or a crossing between each set of pole and zero sets, and this is exactly what's happening here. We have basically one crossing for the red one here, whereas two crossings appear for the blue one here. And it's again the same for here. You can see there are two crossings. So the higher the putty approximation order goes up, the more crossings will appear here. And we can see that the interval is quite off. Because if I use the body plot here, I can directly conclude the upper bound. The negative one works always like a charm, but because it is a origin crossing, omega is equal to 0. If you plug in omega 0, you have just one possibility. But the system model, let me just show it again. The system model using the putty approximation has some problems for the positive or for the upper bound. And the reason behind that is the following. The system tries to model the root locus as close as possible to the actual system with delay. But the issue here is that it's capturing the wrong omega values here. And you can see that the omega value or the j omega crossing coordinate here is changing, whereas the structure of the root locus is also changing. So if you increase the order, you should get a tighter bound, but due to the crossing being not on the origin, it will make some faulty or it will produce some faulty results. So using the putty approximation and the root locus when you are able to use the body plot makes no sense. But you should know that you're doing an erroneous thing. You are accepting that the putty approximation is not perfect. It is an approximation, so the result is also an approximation. Therefore, you should be careful about this. And it is also important to note that instead of giving us the stability interval, what the putty approximation actually does guarantee us is the instability region. So it is it's not stable out of this bound. So greater than 1.86 is definitely going to screw up the system stability. And it's becoming tighter and tighter if the approximation goes higher in order. But yeah, use the body plot version instead of the putty approximation and then root locus, or putty approximation and then the numerical stuff. And keep in mind that I have directly calculated the k values and omega values. If you were clicking on the root locus plots using MATLAB, that would be even more foolish than being or using this so far. because this is a lot of work and the body plot is just based on a simple search of the nearest and taking the inverse of the gain. So yeah, that's it for the stability part here. So let's go on with the second part of our question 1, being to design the PiController. Now, let's actually copy some part of it to a new script. So let's come back here. These seem to be nice. So the first one is the first order putty approximation. So let's start with that. So part 2, putty 1. So this is quite straightforward, but I'm going to quickly go through it. Now we have GS, GSD, we have this, and now what do we need? Well, since we're using the approximation, we have GST, so let me get rid of that, maybe like this. So GSS is going to be the system that we are going to use. Now we have our controller parameters KP and KI. Therefore, our controller will be KP plus KI divided by S. And then the closed loop will look like the following. FSS times GSS plus 1. Now we need PZS and PCS equals num then DSS. And then this would be the result here. So it's a sixth order closed loop. So what we need to do is basically we need to define sims A, B, C, D, E, and F, I guess. These are the real values. Now, I'm sorry. Now, the residue polynomial, of course, we forgot to mention that we have overshoot specification of 10% and settling time specification of, what was it again? 10 seconds. Okay. So, therefore, we know what PDS should be. So, sims omega n, no, not sims omega n, I'm sorry. Zeta equals minus log overshoot divided by the square root of pi squared plus log overshoot squared. Omega n is equal to 4 divided by ts times theta. And therefore PDS is equal to s squared plus 2 times theta times omega n times s plus omega n squared. There we go. Oh, it's a 6th order one. We need only 4. I just overdid stuff again. Okay. So this is going to be s to the power of 4 plus a times s cubed plus b times s squared plus c times s plus d. So the problem is to equate PCS, all the coefficients, to PDS times PS. So let's solve the problem. So yeah, we have 2 parameters there, 4 parameters there, which would make up 6 parameters. Do we have a direct solution? I'm not sure. Let's see. So we have a direct solution. Sol.A, Sol.B, Sol.C, Sol.D, Sol.KP, Sol.KI. So we have everything what we need, And it seems like we can only assign this to a certain point. Oh, by the way, I'm doing it for PuTTY 2 here. Interesting. I missed that, but I'm going to, yeah, solve it in a minute. So, since we have everything we want and we have not that much of options, what we are going to do is we're just going to define our controller here, PiController. So it would be, let's call this double sol.kp, sol.ki. So, well, there are two different transfer functions. Let's call it ts PuTTY2 and the other one. And the reason behind that is that we have basically delay in our system. And if we use the delay here, gs times gs delay here, so gs didn't change, I guess. This would be the closed loop here, but ts2, which is going to be the actual closed loop here, actually I did write it down. It should be GST here. Yeah, that's better. Now, if we use the PuTTY approximated transfer function, of course, it should give us a certain result. And if it works, it should work because you are designing the controller for this transfer function. But the actual result is hidden in the delay version of your transfer function or model, because that is the actual system under control. There is no such system as GST. The actual system is basically GS times GSD. So therefore, we should actually test it on the actual nonlinear system, not on GST itself. But I'm going to show both of them. So let's create actually another figure, but I can, I guess, start counting from 1 again here, and then hold on, grid on. So let's basically look at the step response of TS PuTTY to which is Y PuTTY 2, T PuTTY 2. So this should be Y. Let's call it Y to T2 and TS2. So let's plot them. T2, comma, Y, actually T PuTTY 2, Y PuTTY 2 with black and line width of 2, and of course also T2, comma Y2 with maybe a blue color here. Let's give it a display name. Let's call it PuTTY 2. Let's give it a name here, actual. There we go. So actually, let me change this to that and paste it back again. So this should be PuTTY 1. So let me also rearrange that. This should be the first order PuTTY approximation. The only thing that is going to change is I'm going to define a SQ plus AS square plus ES plus C. There's no need for D. And then hopefully it will solve it. Then we will get FS1. Let's see. GST, TS PuTTY 1. It would be TS1, FS1, GS, GSD. We would plot that. I could also maybe combine them, but for the moment being, I guess it's not that important. So actual body 1. So let's see. Line 27. Line 27. Oh, let me just see if we did mess up anything. Doesn't seem like it. Seems like it's not calculating it. So what about the problem here? Oh, we have a minus sign here. Okay. So we need another variable here. And to be coef, but then again, coef is going to be coef divided by coef1. So we get rid of that negative sign. And now it kind of works. Nice. And let's open up this one here. I'm not sure if we need anything about that. Seems not like it, so there we go. Maybe adding this legend here, even though it's kind of obvious. So interestingly, we can see that we have kind of the system here and the behavior of the system. Of course, we couldn't even look if the dominance factor is good, if it's kind of satisfying our results. It is obvious that we cannot satisfy the results because, first of all, we had a settling time of 10. I can see both of them are not really working as they should be. And second of all, we allowed a 10% overshoot. That's also not happening here. And the problem is that we have just not that much control over our system because KP and KI, we have just only one solution here, and there's no way of optimizing this. But what we can do in order to solve this is basically we can just go ahead and use a PID controller and then enhance the solution here, and because this structure is not capable of handling this. But since this is a homework and the aim of the homework is basically just to recap all the topics that we have available to us. It's just like this. So what happens if I change it to 20 because the aim was basically 20? Yeah, it doesn't really change. Well, actually, it changes. So yeah, if we take TS equals 20, we can see it works, but we didn't do anything to it so that it works. It just works naturally. And this is basically just to for you to just solve the PuTTY approximation, design a controller for that. But actually, if we would have the ability to design something, we would transition to PID. But here we have a comparative study here. Therefore, it's everything is about the PI controller. Ideally, this would have been a question with PID controller. But yeah, this is the solution. If we take 20, it is it works like a charm. If it's 10, it doesn't. But well, we didn't do anything, so it's also not really that important. if it's 10 seconds or 20 seconds. We can see that the second body approximation is exactly on top of that. If we examine the step info, I would say PDS2 or the second order body approximation does a better job, but we don't have too much control over this. We just solve the unique solution, so yeah, we can skip to the next part here. So the Smith predictor is again kind of interesting because here the Smith predictor part is quite simple again, but we'll see. So Smith predictor. So in the Smith predictor, we know that we actually don't need anything at all. We're just going to take the system and use a PiController and then design the PiController. Since the system is a third order system, when we design a PiController, it should be a fourth order system. Two of them are decided. That would mean that we will lose C here. And it would be S squared plus AS plus B. And I'm not sure if I even need that, but let's leave it like that. So let's see what the solution looks like. So we have again a unique solution. It didn't change that much. And it's a stable solution. So let's directly dive into the solution here. So we don't have anything like that. Now the controller SP, let's call it SP, or Pred, let's call it Predictor. So the solution to this is interesting because I'm going to multiply with 1,1 and then IO delay. Actually, we have that, so maybe I can just add GSD here. Because the assumption was that we have a special structure, which you can find in your lecture notes, which I'm not going to go into detail. But we have a special structure which gets rid of the prediction part so that we get a special closed loop transfer function. And that closed loop transfer function was separable into its delay part, which is inevitable in this case. There will be delay, but the remaining part is just a basic minimum phase transfer function. And if I design the PiController for the minimum phase of the open loop, I end up in the closed loop, which is basically the minimum phase closed loop, shifted with 2 seconds delay, and that's basically it. So yeah, I cannot use the delay transfer function here and then connect my controller to it, because that's not the structure. You have to refer to your lecture notes here, but you should remember that the closed loop will look like the minimum phase part of the open loop times the controller, the whole closed loop of that, times the delay part here. So let me just take this, put it on figure 3, get rid of this, and call it Pred. And then there we go. Of course, this is without modeling errors, but I'm looking at the ideal case. If not, I might use the complex transfer function or Simulink in order to simulate this thing. But it's more about the design at this point, because these are design questions than the design itself. And I'm just providing you the solutions here. So now again, the PiController is not a suitable controller for this system. For this system specific, if we choose settling time equals 10, then everything gets problematic. So let me just change that. Body approximation is not possible to use, and it's also not possible to use for the Smith predictor. So if TS is equal to 10, this PiController is insufficient, we should choose PiController to at least optimize something about the solution, because we have just a unique solution. If I increase it to 20, because the system is slow enough, what I can see is I can still see that the PiController, even with this Smith predictor, is not sufficient for the system. We need basically a better controller, or with the PuTTY approximation errors, it favors us, so we can use the PuTTY approximation. But it is not about the Smith predictor, or it's not about the PuTTY approximation. This is just this specific for this system. So don't get a misjudgment out of this, because it seems to be working, but it is due to the differences, and we end up in a whole different result than it should be. Now, the last but not least is to use the body plot in order to design this API controller. Now, I'm going to take this part here, maybe even this part here, and a little bit of this, because I can use it. So let's come to the body plot. So first of all, I'm going to look at the body of the original system here. Let's open up figure 4. And sorry, we have the body plot, and I'm going to comment this part out. Now, now for the body plot, we actually are looking for the Zeta value here, and we have a phase margin here. So basically, there are two approximations about this. One of them is to approximate the phase margin with 100 times Zeta, and the other one is an ATAN formula, which you would recognize from the laboratory sessions, but I'm going to use this one for now. Now, we are looking for an angle here. I'm going to go through the steps here, but I'm not really going to go into detail. So, we are looking for -100 plus phi m, and then we are looking for basically the omega n value here, which index is basically the natural frequency that we have. So omega n minus omega. Do we have omega n? Yep. So this would be the index. And we are going to look at the angle 180 plus phase index. So what is our current phase margin here? And we are calculating a phi max. Is it called phase? Yep. Phi max is the phase margin minus the phase that we have. So this will be basically the contribution here. So let me first calculate them. So phi max. There we go. Now, Kp, the proportional part of our controller, can be calculated using cosine. I'm using cosine d for degrees. It is phi max divided by the magnitude index here, and the ki part here is basically omega index squared times minus sine of d, degrees again, phi max divided by magnitude index times omega index. So let's see if we messed up anything. So kp, ki. So let's basically define our controller. Let's call it body, tf, kp, ki, 1, 0. And then of course, where did we have that? So let's have this feedback here and hold this thing here. So ts body is going to use fs body, and what is going to be the figure? Figure 5 in our case. And going to use y and t, ts body, y, t. Oh, actually, there we go. So let's run this again. So this is basically our result here. Now, there are many papers on PI or PID controller design using body. This is kind of a phase lead controller algorithm. You look for a certain phase margin, and then you look for the natural frequency that you're interested in, which is omega n, directly omega n in this case. And then we have the phi max approach, which we had in the phase lead controller 2, as far as I remember, where we calculate beta. So there's this specific formula here, which you can find out in the literature. And the thing about frequency domain approaches is that it's not really easy to we have to go into theoretical details and prove everything in order to understand it. And most of the time we just accept it and use it as a step-by-step guidance for us. But once you have a step-by-step guide or an algorithm here, it's quite easy to come up with a controller. Even though it's generic, it's still something here. Now you can see this doesn't really satisfy our zeta or overshoot value here. So that would mean that we have too much of a phase margin, or even lesser, depending on basically the situation here. So what would happen? Let's see what the settling time is. It's 20. So let's try it for 10 actually. Let us try it for 10. It's not even stable. So yeah, what we can do is, in order to tune it a little bit, because we're not we cannot really rely on this relation too much. Even if you use the A10 version here, the phase margin can be tuned a little bit. So yeah, let's assume that we are what is phi m, by the way? Phi m. So it's 59 degrees, which is actually not that bad, but yeah, what happens if we in this case increase it, I guess? Increase it a little bit, so maybe 20 degrees. So let's see, is it going to help any? Nah. Let's make a dramatic change here. Is it going to do? Nope. What happens if we subtract a little bit from it? It seems like we're not quite lucky for this occasion here. So maybe we should subtract a little bit more. Let's see. yeah, we're getting somewhere. Seems like this is basically a thing that we should do. So what about 60? Yeah, it didn't work that much. So maybe 55. But that's going to be the limit here for this settling time here. So if it's settling time 10, it's really hard to even get it working. But what happens if we have settling time 20? We get a bit a better result. What was our zeta value here? 0.59. So yeah. So what is phi m? 4.11. Yeah, in this case, we're not really at a good shape. It changes just a little bit, well, not that much. So yeah, it's again not really that easy to come up with a PiController, and we've also seen that the PiController on its own is still painful. So yeah. When we use stuff like that, did we use? Okay, no, nice. Yeah, this is basically the PiController here. Maybe I can show you the paper that I've used here. I don't remember if I have it available somewhere. So let me see. Seems like I have a link here. And yeah, actually I have a nice video here, so I'm going to add that to the description probably. So there's a numerical example to designing a PID controller as I've did it here, but since the system is not really that suitable, it's quite hard to get a very good solution out of it. 30 times theta, I've somewhat note down to use this phi m here. Let me just see if it's going to work. Yeah, it's still not the best solution here. So for some reason I have noted down to use 30 times theta instead of 100 times theta instead of subtracting stuff from it. Maybe we can wiggle around a little bit more to get a better solution, but that's the best we can hope for. We're kind of changing the phase margin here. If I decrease it, it's going bad. If I increase it, let's see what's happening. It's a little bit better, so maybe 50. It's still increasing in performance. Maybe we should increase it a little bit. Well, yeah, it will never be acceptable, I guess, because the overshoot is not 10%, of course. And when I increase that, I'm messing up something else. Now it's shrinking back again. So you can see there's a certain limit to it. So what's going to happen if I have 90 here? So it's decreasing again. So 100 is kind of the limit here. So let's try 110 here. So it's just tuning about, we're just trying to tune the phi m here, but you can see somewhere around 95 maybe is the best value, and then it's just messing up stuff like that. So the closest we can get is like this. You can see the settling time is a little bit off. The O-shoot value is off. Maybe we can also tweak omega n a little bit, increase it or decrease it a little bit. Apply just a coefficient here. What is omega n? It's 0.33. So what happens if I, for example, take 80% of that? I'm not sure. Let's see. You can see tweaking it a little bit changes the thing here. And the reasoning behind that is we have a high order system, and not only a high order system, we have also delay in the system. So these methods in the body plot, or using the body plot, are not really suitable for any system, because you might need to tweak it a little bit, and it has its limits, because we have only a body plot and we don't know what the system or what the body plot belongs to. It could be an aircraft, it could be a vehicle, it could be something else, it could be the human body. We don't really know when we have a body plot and only the body plot, and the design methods that rely on the body plot are quite struggling with the system. But this is the best you can get, because you don't know what the system is, you have just the body plot, and you're using the body plot aspects in order to design controllers. The frequency domain is a very powerful domain, but it gives you only what you can get. Therefore, this would then conclude the part 1 here. So let's transition into part 2. Run 3.m, clear CLC. So let's clear this part 2. So now we have the same transfer function here. So I'm just going to basically take it from here and go here. So this is basically our transfer function. And what we are trying to do is we're trying to convert this into state space representation. Now let me just define sims s. Let me just use tf to sim here. So we have GSS. There we go. Now, if we want to convert this into a state space realization, what we do is we just get rid of the numerator, focus on the denominator, because that's our characteristic polynomial. So let me just take that like this. And it's basically going to be equal to x divided by u, a transfer function between x and u. And if you look closer, if you multiply stuff here, you will see it becomes like this. And we can directly see that it would be the third derivative of x plus 7 times x, the second derivative, plus 9 times x derivative, plus 5 times x is equal to u. Once you have that, all you have to do is leave x to the third derivative alone. So it would mean that we will get rid of this. This is a negative sign. This is another negative sign. And let me move this to the end. Plus u. There we go. Now, if x1 is equal to x, then x2 will be x1 derivative, which is x derivative. x3 would be then x2 derivative, which is x double derivative here in this case. And based on these definitions, what we can do is we can just see and replace everything in terms of x1, x2, x3. So if x3 is x double derivative, the derivative of that would give us x to the third derivative. That would be equal to minus 7 times, actually, what do we have here? x3 itself. So x3, because x double derivative is x3. Then we would have minus 9 times x derivative, which is basically x2, and then 5 times x1 plus u. So we can basically see that we have just one differential equation that is a first order differential equation, and we have also two additional differential equations here. So it would seem like we are almost done here. So let me just get rid of the unnecessary stuff. Let me just rearrange that. So x2 derivative is this, x1 derivative is equal to this. Now I can also write down the matrix version here. So if you look at line 10, you can see 0x1, 1x2, and 0x3. The next line, x3, has no x1, no x2, but only x3. And then the last line here is basically minus 5, so minus 5 times x1, minus 9 times x2, and minus 7 times x3. And we can see that the first two equations have no u in it, so 0 times u, 0 times u, but the last one has just 1, so that's going to be 1. Once we have done that, since we did get rid of everything else, we know that we need to have 4 times x divided by u in order to get y divided by u here. And the reason behind that is that 1 divided by the denominator here is already x divided by u. 4 times that should give me the transfer function. If I multiply with u, I'll see that actually y is equal to 4x. And in terms of x1, x2, and x3 here, I can see x is equal to x1, and therefore I can conclude that c is going to be only in terms of x1, so 4, and no x2, no x3. And there's also no u at all, so it's going to be 0 times u. So therefore I kind of worked my way out here, and I got what I wanted, namely the state space realization. So I can check if my response is correct. I'm not sure if this works, but let's see if it works. There we go. This was our original system here, 1795. You get the same transfer function. So this is basically a valid transfer function. And if you want to use the symbolic toolbox, what you can do is you can do C times inverse of S times the identity matrix 3 minus A times B plus D. So it's also possible to use the symbolic toolbox. It will give you the symbolic version of it. So, having said that, let's continue. Let's move on with the next task here. Design a state feedback controller using the assumption that all the states are measurable. Plot the closed loop step response and the states. I'm sorry. Now, we are asked to design a state feedback controller. So state feedback controller. We have a third order transfer function at hand, which means that we are going to design a state feedback controller that will have 3 coefficients, and we need 3 poles. Just for the sake of simplicity, I'm going to choose the poles -1, -2, and -3. The state feedback controller can assign all the poles of a polynomial as you wish. You can just choose any combination of poles and you can assign them. The only restriction is to have a controllable system. You have to check the controllability matrix. If it's controllable, if the state space representation that you have at hand is controllable, you're good to go. So, the controllability matrix, since we've talked about that, is B, A times B, A times A times B. And if we look at the rank or the determinant of phi C, or if we take the inverse of phi C, if it's possible, we should the system would be controllable and we would be good to go. Seems like we have a full rank matrix, or we can even compute the inverse, or the determinant of phi c is not equal to 0. So therefore, we can calculate or design a controller as we wish. So that's one part of it. Now, what if we have basically poles? The first step is to use these poles in order to come up with a polynomial that would be the desired polynomial here. So we need a PDS here. So how can I do this? Well, if I do S minus poles, so let me just do that. I would get this. And if I use prod, I guess, I'm not sure, I'll see, we get the product of it. So this is quite nice. Now, I want to substitute in basically S equals A, but the problem here in MATLAB is that if you do this directly, you will get a wrong answer. And the reason for that is that it is possible to add a scalar to a matrix in MATLAB, and that would happen by element adding them together. So instead of doing that, I need to get the coefficients of PDS. And what I need to do is define PDA equals 0, for I equals 1 to length of the coefficients here. I'm just going to do the same. PDA here equals PDA plus a to the power of let's call it, oh, we need the order of it, okay. So n equals length of coef minus 1, so n minus I plus 1 times coef. So coef I. So let's see what PDA looks like. So this is not the same as this one here. You can see it's not the same. And the reason is that it will add it element by element. So now our state feedback controller would be the following: 0, 0, 1 times the inverse of our controllability matrix times PDA. So of course I need to convert it into double, and due to this one here, since the coefficient is not a double, I guess it doesn't give us that. Okay, now how can we check if this is basically a valid controller, or if we didn't mess up? Well, we have to look at A minus BK here, or I guess in this case maybe plus here. No. Oh, seems like we did mess up. So the inverse of that times PDA. If I is equal to 1, it will get rid of that. Nice. But for some reason, so what about Paul? This shouldn't actually mess up. Interesting. Oh, maybe it is because that. I'm not sure, but it's probably because of this. Yep, there we go. We needed to put that there. Okay, now we can see that the eigenvalues of A minus BK are -1, -2, -3, which directly concludes that we have assigned the poles to these values. Now, what would be the closed loop if we have such a system? Well, the since we have dx equals ax plus bu and y equals cx plus du, if we plug in u equals minus kx plus r for reference, what happens is that we get this here, and this would end up in being minus bkx, and so yeah, minus bkx plus br, and if we plug it in here, minus dkx plus dr would be then the result here. So you can see that we can factor it out. A minus bk is going to be this, and of course we have c minus dk, which would give us the closed loop here. And we can apply step to r and see what y is going to be. So therefore we have again b, c minus d times k, and then d, and we can convert it into a transfer function and get rid of this, and then look at the step response of that. So if I run this, there we go. Since we've used -1, -2, -3, all the pulls are real and there will be no overshoot. We can also use some PDS and then also maybe a third pull that is far away. That would give us also something, but we can see that this would be basically our transfer function here, and you can check the roots of the transfer function. 1, 6, 11, 6. You'll see 1, 2, 3. So this is basically the state feedback design. Now we have the Lundberger observer. So let's quickly address that one too. So if we want to design a Lundberger observer, we can basically take the same approach here. By the way, we have also the Ackermann formula. This is basically the Ackermann formula, but you also have a command called Acker. You can use that or place, but I'm not using that because I want to show you the steps. So Lundberger observer. So here, instead of using phi c, we need the observability matrix. And it would look like c times a, c times a times a. And then we also need to address the pulls. Now, -3 is the fastest pull here. And times 5 times 10 would be a good thing. Let's say times 5. So I would choose -15, -15, -15 here. Because the observer should be faster than the controller and even faster than the fastest mode or fastest pole of the system. So you can kind of guarantee that you have observed the states before you control the system, before it is over. So I'm going to construct the same PDA here, but instead of that, we will have basically the inverse of phi o PDA, and then 0, 0, 1 should be it. So the eigenvalue of a minus L times C should give us the roots that we are looking for. So you can see -15 approximately, -15, -15, it has some sensitivity because we've chosen them on top of each other. Maybe a better choice because of the sensitivity could be minus 16, minus 17, just to have a little difference there. You will see minus 15, minus 16, minus 17, exactly at the point where it should be. Now, what is the controller capable of, or what would be, what is the observer good for? Why would we use it? Etc., etc. Now, let's say we have ax plus bu, and y is equal to cx plus du. We're basically copying the system here, which is called the observer here. So let's have an underscore for that. It shares basically the same here. So what I'm going to do is I'm going to basically add another term here, the correction term, basically, plus L y minus y. So basically what we are doing is we are taking the output of the system, we are using our own output, we take the difference, feed it back to the observer. Actually, is it minus? I guess it is minus. Cx minus, yeah, it should be minus. So, now what happens is that, let's don't think about u for a moment here. Let's plug in that y is equal to cx plus du. Therefore, we have the same for this one here. So this should be minus du. So you can see du's cancel each other out, and we're left with this here. And if you factor out that, you would get basically L times C x and x underscore here. If we rearrange that a little bit, so we have minus LC times x and plus LC times x, like that. So this comes in here. So we have A plus LC times this here plus BU. Let us just bring it back here. Like this. Maybe this one should also be on the left. There we go. Now, we can actually combine these two dynamics to each other as a whole big system here. You can see we have dx here, we have dx underscore. So if we define a xx underscore state vector, we would end up in something that would have an A matrix like A0 and then 0. Actually A0 and then minus LC and then A plus LC, I guess. But I guess we messed up the negative signs here. Should be something like this. LC and A minus LC. And for B, we would get actually, we have B for this first system and B for the second system, because they will take an effect there. Yeah. Now, therefore, we can define a bigger system here. Let's call it sys. And we can just put the multiplication sign here. Let me get rid of everything here. So what we can do now is, I'm just not going to name them A and B. Let's call them AC and BC combined. So AC comma BC. And then I'm going to just provide a identity vector here of 6. And the reason for that is 3 states of the original system, 3 states of the observer. And then we will have a zeros vector 6, 1, because D is already 0, so I'm not going to bother with that. As far as I remember, yeah. So it should be 6, not 5. So now, now we need to simulate this. Yeah, and therefore, as far as I remember, there's something called initial, and we provide the initial condition and the system, and it will just create a plot for us. So can I, let's see, so y comma t, or even x comma t, initial, and then provide the system, and then the initial conditions here. So in the PDF, you can see that actually here with the controller, but I'm doing it without the controller here now. You should provide initial conditions to the system, but 0 initial conditions to the observer here. So let's do that. Let's have, for some reason, ones, 3, 1, and then maybe 10 times ones. So yeah. Let's see if it works. It says that, oh, this should be a zeros times a 3 by 3 0. Of course, now we have x, we have lots of states. So what I can do is I can just create a figure. Let's call it 2. And create a subplot, 3, 1, 1, because we have 3 states. And I'm going to plot t, comma, all the columns, first column, line width of 2. Because this will be the state of the system, this will be the observer, plus 3 should be okay. Hold on, grid on, x label should be time, and then title should be x, 1. So I hope I can use a for loop here, 1, 2, 3, to generate it automatically. So this should be I, this should be I, this should be I, and then this should be I, and we should be good to go, I guess. So there we go. Now I have generated this, and the whole thing about the system is that we start at 0. You can see we have a certain time to adjust our states so that we match the states, but it takes some time. And if I have a certain setting time in my mind, I should basically take this into consideration because it takes some time. And during this time, which is not really that bad for this case, if I have, for example, something along 3-4 seconds or even 2 seconds in my mind, it's not bad because it takes just almost a second. Of course, it should be even better, but yeah, it takes a little bit time to estimate the states. And during this operation, I'm trying to use the false information. If this is a special system, for example, I'm over reacting to the system on the controller side because I think that this state is, for example, as high as this, whereas this is not the case. So the same goes for x3 here, whereas x1 is not really that bad. You can see that the initial conditions are quite important if you think about it. Therefore, we should be aware of that. The faster the system is, the even faster should we design the observer to avoid these effects, these possible effects. So as far as I remember, I should also be able to do this for the controller case here with controller. And since I'm going to use the state of the observer, I should write down u equals k times x underscore instead of k. So if we have bu, this will be b times k x underscore. And since both are added to these here, so I should probably add, so this is with controller, let's make it 3. So this should be basically the second part here. It is minus kx, so it should be minus bk here and minus bk here. If I'm not mistaken, this should be basically it. But I'm feeding both out of the observer, so we'll see what's going to happen here. So this is a figure. This is another figure. Did we accomplish stuff? I'm not sure. So did we? It should change behavior. And I'm feeding back the system out of that. So what is the k value here? Maybe the k values are not really that influential at this point. So maybe we should take an aggressive route here. Let's change basically the poles. So let's take a more aggressive route, maybe like -10, -20, -30. Of course, we should also increase the effect of these. Maybe let me just choose dangerous poles for the observer. And let's see if it's taken an effect. Yeah, now we can see the effect here. The one on the left is basically open loop. The one on the right is basically closed loop. And I don't really know which state I'm controlling for now, but I'm changing the behavior. We can see that. And well, it's not ideal in terms of the observer because we need a little bit more speed here. So let me just speed it up a little bit more. So you can see it kind of affects the system at this point. Of course, this is an initial value problem. If we want to see the effects even clearer, what we have to do is we have to put in an integrator and then a reference tracking problem. And then we should look at the problem here, or the system and the observer and the controller performance here. But that was not asked here, so I'm going to stop at this point. Hope that this video was helpful and you did learn what the homework solution was. So see you in the next videos.